gatherings, yes.
Hi, everyone. I'm delighted to kick off the 2022-23 academic year with a talk in person and virtually by Santosh Nagarakatte. Santosh did his PhD at the University of Pennsylvania, finishing up in 2012, and has been at Rutgers since then. And what he's going to be talking about today is some very distinguished work, which is the basis of two distinguished paper awards at the PLDI conference, as well as his student Jay Lim's Programming Language Dissertation Award, the John Reynolds Award. So it's a really impressive way to kick off this series. Santosh.
Thanks, Matthew, for the introduction. So today I'm going to talk about the RLibM project. An alternative title is how we build the world's fastest math libraries and what are the key ideas behind it. Okay. So again, I want to, one of the cool things about in-person talks is interaction. So I would love interaction. And Matthew has kindly agreed to relay Zoom questions to me. So if you have Zoom questions, send it on chat. So Matthew will stop me at appropriate points and I'll answer your question. Okay, so what is a math library? So math libraries are a collection of elementary functions. Elementary functions are functions of a single variable involving addition, multiplication of logarithms, trigonometric functions, and polynomials. Who uses them? Everyone uses them. Like if any aspect of scientific computing, any aspect of physics, like whatever you do with computing, like if you're dealing with real world, you use math functions. And for some of you, the students out there, like and interested in machine learning, e power x is kind of your savior, right? So you use it everywhere, like fast Fourier transforms for natural language processing and like translation, and sigmoid functions for your activation. So everyone uses them. So unsurprisingly, like all mainstream libraries have implementations. Okay, they're like 50, 60 years of work. Unfortunately, they are all wrong. Okay, what does it mean for it to be wrong? So this is like the kind of errors in each of those functions, how much error you have for each input in the GCC's libm. GCC provides libm, right? So you would say like, who cares? Like my machine learning model works, right? So I will tell you like two instances. One, like you are a student, you trained your next favorite like billion parameter model, and you had a fantastic NVIDIA GPU. It had 85% accuracy. You are jumping with joy. And then you run it on an AMD GPU, the accuracy tanks to 25%. And now, good luck debugging it. Okay, so this is just a if you think this is a hypothetical example, go to NeurIPS 2017. There is a keynote by Ali Rahimi. He won the Test of Time Award. He was giving a keynote there, and he has an anecdote. So there was a production model deployed in a production at a particular company, and the production model had an accuracy of 85% or 88%. And then he gets a pager call from his team member. Oh, I changed the rounding mode in TensorFlow to round to 0 because it's really effective for some of the custom hardware that they have built, and the model accuracy in production has tanked to 25%. And so these are very common. Now, like you are the engineer entitled with debugging this model, good luck, right? So our goal is to build correctly rounded elementary functions. Okay, so this is an area that involves like numerical methods, algorithms, approximation theory, mathematics. I work in none of these areas, right? Like I'm a programming languages, compilers, formal methods person. Let me tell you a story about how I got excited about this area. So a long time ago, I was building formal verification tools for compilers. Compilers are million lines of code. They are critical components of all your entire computing ecosystem. If your compiler is buggy, a small bug in your compiler, what would happen? You have your correct program, you would produce foobar results. So we wanted to show the correctness of compilers, use formal verification. So we formalized the semantics of a widely used compiler LLVM. And then what we realized was no one is going to use it. Because like if you make verification so hard that you have to spend like 100 people to verify small components, no one is going to use it. So one of the cool things that I did with my PhD student, David Menendez, was we designed domain-specific languages to specify compiler optimizations. Okay, and then we would automatically translate them into first-order logic formula. And if the first-order logic formula is valid, it's correct for all inputs, implies your compiler optimization is correct. And then you generate code. And again, you can't do everything, but we chose subsets where we can do a very good job and showed value for it. And my student wrote a slew of papers. He also won the John C. Reynolds Outstanding Dissertation Award. And more gratifying thing, like now looking back at it, like 5 years later, is it's now widely deployed in practice. If you want to get a new optimization into LLVM, it's checked using Ally, which is our domain-specific language and a verifier. Okay, it's used by 12 companies in production. Okay, this is what we were doing. And David verified integer optimizations. And then every compiler has floating point, has to translate floating point. Your code is in floating point, right? You are approximating real numbers. The compiler optimizations are of two kinds. One, I don't want to do anything with floating point. Like, oh, floating point hurts my head. Like the most compiler optimization developers say, I don't want to touch floating point. Okay. And then there are the other kind. I want speed. I don't care. So I'll treat any identity that is true with real numbers to be a floating point identity and do those optimizations. These are called as fast math optimizations. My alternative name for them is unsafe math. But that's what like people use it, like fast math. Okay, so again, reasoning about fast math is very challenging. Like it's more, so David focused on just verifying bit precise optimizations. Like, oh, is this optimization compliant with IEEE 754 standard, like bit by bit? And even when compiler developers did not want to do anything with floating point, they got it wrong. So they changed the sign of 0. And like, if you don't know, like floating point has 2 zeros, positive 0 and negative 0. And you may wonder, who cares, right? And William Kahn, Turing Award winner, has a fantastic journal article on how changing the sign of 0 changes branch cuts with some complex elementary functions. Okay, so this was all cool. And then I had an amazing set of undergrads. Like 2017, like I was hiring a lot of undergrads, and they were excited about machine learning. So, and then I said, like, I can't advise students on machine learning. I advise people on compilers, right? So, okay. So my students said, like, there is fast math optimizations. Can you measure? Can you look at like how do machine learning models operate with fast math? So this student like took a curated data set, a custom support vector machine learning algorithm that he had learned in his class, and he trained it. And exact same algorithm, exact same data set, same number of iterations, time for training. And all it changed was the compiler flags. The accuracy is significantly different. Okay, so now recall just like one slide ago, I told you, if you are the person entitled with debugging large models, good luck. Right, so now we were caught up with the same scenario. My student had to now debug. Okay, so we didn't have tools. How do we go about doing it? So this is where we built shadow execution tools. So effectively you have floating point execution, and then you should have an oracle. Let's say the oracle is with real numbers. So we would compare both these executions lockstep. Every instruction we compare. What did the floating point execution produce? What did the oracle execution produce? And where did they diverge? Okay. And surprisingly, in many cases, we found the first place of divergence was with elementary functions or math library functions. You call e power x, like you'd have small errors, and later on they get amplified. And it results in crashes, your entire thing becoming NaN, so your model accuracy tanks. So who cares? Like, well, like if you're a debugger, debugging it, like it matters. And the second important thing is like portability. Like you take your application, you cannot run it on a different machine, you'll not get consistent results. Okay, so how do you go about go about handling portability, reproducibility, and various aspects? And this is where I got excited about. Why are these elementary functions producing wrong results? People have put in a large amount of work designing them, right? Like 50 a body of like 50 years of work. And why are they wrong? And now, like what I'm going to tell you is that the key insights in the RLibM project, and like I will make it as self-contained as possible. But if something is not common to, if it's not understandable, please ask me a question. So yes.
A couple of slides ago, you mentioned the next error. What was the units?
It's ULPs, units in the last place. That's how you measure floating point errors.
Okay.
So what you do is a floating point representation is of some k number of bits, right? So how many bits are actually wrong? So one ULP error is the last bit of your representation, and the representation is wrong. So if you have like two ULP error, like last two bits are wrong. Okay, it's generally log log the ULP error to base 2 is the number of bits that are wrong. Okay, so they get amplified. Like even though like it looks like very simple, right? Last one bit is wrong. How does it matter? But it eventually gets amplified. Okay, so what is a correctly rounded result? So you have a real number line. There are infinitely many real values. And with any finite precision representation, you're approximating infinite number of real numbers with a finite precision representation. So let's say 32-bit floating point. So they can only represent finitely many points. Here, V1, V2, V3 are finite precision, are values representable in your floating point representation. Okay. So now you have an elementary function. Let's look at ln of x1. Okay. So it produces a value. So ln of x1 is an elementary function. By generally, like it produces an irrational value. So it's not exactly representable in your floating point representation. So what do you do? So floating point is a standardized, like it makes all implement. There's an IEEE 754 standard that ensures portability. So now what do you do when you get a real number like this? You round to adjacent values. So there is something known as a rounding mode. Okay, the commonly used rounding mode is round to nearest ties to even. Okay, so common sense, right? Like if you have 10.5, like you just want to hand out dollar bills, like you would round it up to 11 and give it to the cashier, right? So exactly similar. There are few subtleties like about like maintaining statistical average properly. So this is round to nearest ties to even is your commonly used rounding mode. So if you compute ln of x with the best algorithm that you have and compute it, and then do the final rounding to floating point, you get V2. So V2 is your correctly rounded result. Okay, if your library, if your elementary function produces correctly rounded result for all inputs, okay, so then it's a correctly rounded elementary function. Okay, so now the question is, why are existing implementations not producing this correctly rounded results? Okay, so to understand this, we need to look at how do people build approximations for elementary functions. Okay, so you have e power x, you want to approximate it over the entire floating point input range. So what is the range of floating point? Anyone? So it's 2 to the power of 128 to 2 to the power of minus 149. Very large range, right? So you want to approximate e power x over this input range. So the standard approach that anyone uses results from approximation theory. There is a fantastic body of work from the 1800s in the math, right? So how to approximate elementary function. The first thing I want you to remember is everyone approximates the real value of f of x.
Sorry, IEEE floating point standard, are you saying that the is also the digits for the matrix is from the approximation?
So I think like we are not like now we are just saying let's forget about the IEEE standard. Like we want to approximate e power x, and now how do people do it? And then how do they produce a result for IEEE 754 representation? And then why do they produce? Yeah, so in two slides you'll get it like how do we produce results for IEEE 754 representation. Okay, so we want to produce correctly rounded result for a 32-bit floating point. Okay, and the range is very large. First thing. Now, how do we go about doing it? So before you think about floating point, what do people do? Now we need an approximation technique. So people use ideas from math. Okay, so they approximate the real value of f of x. So there is a fantastic result So if you take real analysis course in the math department, there's a fantastic results called the Weierstrass approximation theorem. So what does it say? If you have a real valued function f over an interval ab, there exists a polynomial that minimizes the maximum error, such that the error between the approximation and the original function is bounded by some epsilon. Okay, this is why. Sorry. So Taylor expansion is okay, but Taylor expansion is like coarse. So you want like more precise. This epsilon has to be very small, right? Like Taylor expansion is one way to do that, but it's a very coarse approximation. So Bernstein's polynomial is a much better. So I think that the goal is like you want to be as close to the real value as possible, so that like you don't change the rounding boundary. That's a good. It's for the entire. Like again, now the question is over a closed interval AB. That's what Weierstrass says. And then this is 1800s, results from the 1800s. Then Bernstein polynomial is a proof of this existence. And then what Chebyshev conjectured, what are the properties of this polynomial approximation, right? So Chebyshev said, if you look at the error function, so f of x is the elementary function that you're approximating, and the polynomial that you're generating of degree n is Pn of x. So now look at the error function, the absolute value of f of x minus Pn of x. This error function is going to have n plus 2 extrema. And this is going to oscillate inside. So this is a conjecture that Chebyshev did. So this is known as the Chebyshev's equi-oscillation theorem. So it's like it's going to oscillate. Okay. From this, you can create a system of equations and solve it and identify the polynomial. So, and the algorithm to do this is the remiss. So the point is, you can generate a polynomial approximation over a small range AB, such that you have some bound on the error. So these are results from approximation theory. Okay. So as Kostas was alluding to, come on, there's some catch here, right? Like you said, floating point is 2 power 128 to 2 power minus 149, and you said AB can't be that big, so you have to do something. So polynomial approximation is feasible over a small domain. So generally for ln of x, it is only feasible between like let's say 1 to 2.
For what? Sorry.
Between the range 1 to 2. Or like you have to reduce it as small as possible.
But there's also another design parameter, the error, right? If your error bound is much larger, you can go with a coarser bound. As you
Sure. There are like it's a large design constraint. So again, like depends on what context you're looking at, right? With correct rounding.
So firstly, why don't I start with that and say what that decision that error bound, what polynomial
So again, so I think there are two issues with IEEE. Like so when you start with IEEE, you have discrete points. Like how do you design an approximation like that works for all points? That's not like you don't have any results in it, right? Like so generally what people rely on, like you can quantify an error function with real values. So you otherwise like IEEE is a discrete function, right? Like every point is like discontinuous. So how do you go about quantifying? It's reasoning is hard. So people, that's why we reason with real numbers and then translate them into a IEEE floating point representation, so that is as faithful as possible to the real results. Okay, so
do you want to approximate ln of x by single polynomial or by collection of?
So you could use splines, you could use piecewise polynomials, whatever. Like again, yeah, it's up to you. So you could divide it into multiple ranges and do those, but still it's hard. Like 2 power 128 is a very large value, right? You can't like if you split it up into intervals that are 1 of unit weight. So it is going to have large number of polynomials. So the message I want to give is you have to reduce the domain. Okay. So the first step in a math library is to do range reduction. So use the identities of the elementary function to reduce the domain from a very large domain to a small domain. So how would you do this for ln of x? So let's say you got like 1024 or 1024.5. So you would reduce the way you would translate it as 1024.5 can be written as 2 to the power of 10 times something, value between 1 to 2. So now 2 to the power ln of x is ln of 2 to the power of 10 times ln of some other value x dash. So now use ln of a logarithm is addition of the logarithms, right? Individual components. So it will be 10 plus 10 times log 2 to base e plus 10 ln of log of x1, ln of x1. So this is range reduction. Now the goal is using the mathematical identities of the elementary function, you reduce a large input to a small domain, which is between 1 to 2. Okay, so now the goal is to generate polynomial approximation for a smaller domain. And you do this using ideas from Chebyshev equi-oscillation and Remes algorithm. Okay, and the common strategy what everyone uses is called as a minimax polynomial. It minimizes the L infinity norm. So it minimizes the maximum error across all points. Okay, so you generate a minimax polynomial. And now what do you need to do? Now you got a result for the small domain. You need to compensate the result to produce the result for the original input. So you had x, from it you got x dash, which was a reduced input in the small domain. And you use a polynomial approximation to produce y dash, which is the polynomial approximation for the small domain. Now you need to produce y, which is the result for x, ln of x. So this process is called as output compensation. Okay. So now the question is, as Badri was highlighting, like what are the issues with IEEE, right? The first, when you do minimax approximations, you're going to have approximation error. So what does Weierstrass say? You can generate a minimax polynomial, the error is going to be epsilon. Okay. So then you're going to implement range reduction, polynomial evaluation, and output compensation in IEEE 754 floating point. So you're going to have some additional rounding error. Okay, so if this error exceeds the rounding decision boundary, you get wrong results. Okay, so let me pictorially show it. So this is a real number line again. V1, V2, V3 are all the points representable in IEEE 754 floating point. Let's say for an input x1, V1 is the correctly rounded result. Okay, so your real value happens to be this blue dot. This blue dot is very close to the rounding boundary. So in this case, it's very close to the midpoint of V1 and V2. We're looking at round to nearest ties to even, right? It's very close to the rounding boundary. So the amount of freedom that you have with your approach, with the approach that I described, minimax polynomial, is shown in this gray region. So this is the amount of polynomial error that you can tolerate. And now, as Badri was highlighting, you do output compensation and range reduction with your finite precision representation. It introduces rounding error. It goes beyond the freedom that you have. It produces wrong results. And this is precisely why existing approaches produce wrong results. Now you may say, okay,
Wrong result.
this is why you are late for 10 minutes, but I'll repeat it again. So, so you have finitely many points. Now, like you compute it with computer result with infinite precision, and then do one final rounding. If you produce that result, that's a correctly rounded result. So let's say you compute ln of x with infinite precision and do one final rounding to the floating point representation. That such a result is known as the correctly rounded result. If you produce any other result, that's a wrong result. Okay. So now this polynomial approximation error plus any rounding error in your evaluation and output compensation causes wrong results. Okay, so you may say, let me increase the degree of the polynomial so that like I reduce the approximation. So that's possible, but you pay in terms of performance. Like you can create for sine of x, you can create a 17th degree polynomial, so you reduce polynomial approximation error to be very small. And then you can do clever tricks with range reduction and output compensation so that you reduce floating point error, but it's going to be very slow. So what I'm going to demonstrate now is our approach where we are able to generate like degree 5 polynomials. And that's like 2x faster than whatever people have been doing.
So historically, before this work, where were the sources of the most error?
So
From the final round, was it from the
both. So,
did one of them have more error than the other one?
So I think its polynomial approximation error was so people typically want like good performance with math libraries. So they would not want like polynomials of degree greater than 10. So as a result, like the polynomial, the amount of freedom they had with polynomial approximation was very limited. And then I think like polynomial evaluation, there is some error, but like there are a lot of techniques to address it.
Are there any anecdotes where this actually affected people? Like,
Well, this is why you missed like all the. No, I think like that's okay. So jokes
What
aside.
I'm saying is Mars, instead of going to Mars.
So I'll give you.
Jupiter.
Yeah, there are like Patriot missile which failed. Like there's a nice report from GAO. Patriot missile failure. So there was a system in 1991, like that's attributed to floating point error. Okay, so for math libraries particularly, you may be really interested in it. So NeurIPS keynote, like NeurIPS is a top conference in machine learning. In 2017, Ali Rahimi gave a keynote. Ali Rahimi is won the Test of Time Award. In his talk, he was talking about a machine learning model deployed in production, had an accuracy of 85%. And all he did, like his subordinate did, was he changed the rounding mode in the TensorFlow implementation to round to 0. And why? Because round to 0 is very good for the custom hardware they are built. And the production model accuracy tanked to 25%. So this is like, it's on YouTube. I sent the link to Rich, but I can send it to the entire faculty if you're interested. But like, this is where people are. And we have had like our own frustrations in the sense debugging and dealing with it. Okay, so moral of the story, people are building on the shoulders of giants. They're approximating real values for creating approximations for elementary functions, and they're producing wrong results. Okay, and now is the key message of the RLibM project. In retrospect, it's very simple. And it's also another way I put it is because our key insight is not having a math PhD. So I have a CS PhD instead of a math PhD, right? So the first thing when we started exploring it, so you are dealing with IEEE 754, as Badri was highlighting. Why are you focused on approximating real values? So people were up, oh, let me generate a polynomial that is very close to the star, right? That's not your end result. What is your end result? Your end result is to produce this green dot, which is the correctly rounded result. And what do computer scientists, compilers people do? Directly go after it. So directly, so our key message in the RLibM project is directly approximate the correctly rounded result. Now, you may be wondering, man, Santosh is beating me around the bush. You said like, to know the correctly rounded result, what do you need to know? You need to know the real value. How do you know the correctly rounded result? Like how do you, like given a random input, how would you know the correctly rounded result? You wouldn't, right? So you need to know the real value. So we split the problem of generating correctly rounded and efficient math libraries into two parts. The first part, the task of generating an oracle. Okay, so which may be very slow, which takes like years or months.
Sorry, maybe what about well-known constants?
So yeah, so there are people like pi and E are well studied. Like people have built like already their oracles for them. So why reinvent it again? So there is the task of generating the oracle, and there is a large body of work, like 70, 80 years of like computing history, like where people have built oracles. So you split the problem of generating the oracle. Once you know the oracle, you can use the oracle and to generate the correctly rounded result. But why won't you use it in practice? It's very slow. Just one call would take like days, right? So then once you have an oracle, that's when we directly approximate the correctly rounded result and generate efficient libraries. So this is the key insight behind our RLibM project. And this is what we address to solve the table maker's dilemma that was posed by William Kahn. Like William Kahn, Turing Award winner, he said, why is it hard to build correctly rounded libraries? This is hard because you don't know a priori what is the precision that you need to produce correct results for all inputs. And this is the problem of generating a good oracle. So by splitting the problem of generating the oracle from the task of generating efficient implementations, we have a technique now to generate fast correct libraries. So we need someone to give us an oracle. Okay.
So the decoupling you're doing here is that you're solving you're solving the problem for slowly, and then you're gonna come up with.
Yeah, someone has already, like people have already solved generated oracles, which are very slow. Okay, but they wanted to do two things: the task of generating the oracle and also doing it fast simultaneously. And doing it together makes like you have to make now you can't generate correctly rounded results for all inputs.
So the responsibility of the oracle is not to come up with a real number, is to come up with a rounded result directly.
So the responsibility of the oracle is to again come up with a correctly rounded result for a particular target representation.
Is the oracle supposed to come up with a rounded result, or is the oracle supposed to come up with an infinite precision that?
So I think I think like when I say an oracle, the oracle needs to produce the blue star.
Okay, the real.
The real value. But like once you have the real value, you can just do one rounding to the target result, and you want the oracle to be as faithful as possible. Okay.
Okay, do you want your oracle to give you the lowest star or your?
So I think like for our approach, like if you give the blue star, we'll compute what the green star is, because that's just application of IEEE rounding.
Sure, but if I give you the green.
And that's even more easier. So, but like our process, whether given blue star or green star, it computes what the green star is, green dot is. Okay.
So the question here is this an easy problem if I give you info and I give you real number and just tell me whether this real number is a smaller than info or not?
So there is something known as a Zivs rounding test. So that's what people deploy. Like you produce the way people like I skipped over a lot of details in the past work, right? How do you like when you're doing things on the fly? How do people actually generate results, right? So they hypothesize. Let me do it with like some 32 bits, the precision of 32 bits, and compute the result. And then they apply the Zivs test. Does it like if I just like add an epsilon error to it, does it change the rounding decision? If it does, then my result is not stable. So they do it with 64-bit precision. And this is called as the onion peeling approach. And there is a Zivs rounding test to determine, given a real value and a precision, is it like the correctly rounded result or not? But like if you do this, like you're sacrificing, you're doing it during production, right? Like when you're deploying, like why should you do that? So our philosophy is with RLibM project is you want fast libraries. Someone has already given you an oracle. Let's quickly do it. Like quickly build such fast libraries. Okay, so the message I want, again, a lot of details, right? Like the key thing I want you to remember is if you want to approximate correctly rounded, you want to build correctly rounded math libraries, directly approximate the correctly rounded result. So why is this possible? So if you look at the correctly rounded result, and if you look at the real number line, there is a range of values around the correctly rounded result. You produce any real value in this range, it will round to the correctly rounded result. So here V1, V2, V3 are representable in floating point. So and you're using the rounding mode, round to nearest. So any value from the midpoint till here will round to V2. Anyway, any value from the midpoint of V2 and V3 from here to here rounds to V2. So this is the freedom that you have. Okay. So when you implement a library for 32-bit, you implement it in 64-bit. So there are a lot of double values, 64-bit values between the two floating point values, which is your freedom. And the point to note is if you remember the figure, this gray region, the freedom that we have with the RLibM approach is substantially large than the freedom that I had here. Like, look at that freedom. Again, this is cartoonish figure, not according to scale, but the freedom is much larger. Okay, so when you have a lot more freedom, your polynomial generator will have a lot more freedom to generate lower degree polynomials. Okay, so two key points. One, directly approximate the correctly rounded result. Second, there is an interval of real values around the correctly rounded result. You produce any value in that interval, it rounds to the correctly rounded result. Now the task is, how do you generate a polynomial that lies within this interval? So the lower bound of the interval is L. Let's say the upper bound is H. Now you have a point X1. You want the polynomial, which is P of X1, to lie within this range. You have a linear constraint. Now you have 4 billion inputs, 4 billion linear constraints. Use an LP solver to solve them. That's RLibM approach in a nutshell. Okay, so let me describe the entire algorithm. You have an elementary function f of x, a representation 32-bit floating point, and a rounding mode that you're looking at. What do? We use the oracle and compute the correctly rounded result of f of x for each input. Okay, those are all the dots there. on the figure. And then what do? Then we compute the rounding interval for each of these input points. Okay. So now once we do that, like you can forget about the correctly rounded results. We don't care about it. So now all we want to do is generate a polynomial p of x. What is a polynomial? C0 plus C1x, C2x squared, so on. C1, C2, C3. The coefficients are what we were trying to learn. X is like the inputs that are given in a particular representation, right? So you have a system of linear constraints. Okay. And so now use an LP solver to solve it, and you'll get the coefficients. And so 4 billion. The 4 billion rows, but like number of variables is 5 or 6. So that's a great point. Like keep in mind, this is a linear program of small dimensions, and we have a cool algorithm that I'll describe how to solve it. Okay. So what's the time now, just to get an idea?
It's 10 past 11. So
Okay.
15 minutes.
That's good. So okay. So directly approximate the correctly rounded result. Then there is an interval of real values around the correctly rounded result that imposes a linear constraint. You have an LP problem, solve it. There you go. You have a function, a polynomial that produces correct results for all inputs. Okay. So at least if you have one representation, one rounding mode, now we have a method to solve it. Life would have been ideal if there was only one representation and one rounding mode. But like everyone is designing their own representation. Why? Performance. You want to do your face recognition very quickly, right? So people want amazing floating point performance. So they're designing like various things, various representations, trading off the dynamic range and the precision. So
I got a question. So are you trying to generate a single polynomial with a full range?
Yeah.
Or are you trying to break it up?
So I think like by default, we try to generate a single polynomial over the entire range. Okay, so that's like our, yeah. So it's again, like in a few slides, you'll see things that are deployed in production, which is like single polynomial, 5 coefficients. It works for the entire input range.
What about 64 bits?
So 64-bit, how do you do this? It's a open question. We are still working on it. So hopefully in another 2 years, like I'll have a solution. Okay, so the moral of the story is like we now have a technique to generate correctly rounded libraries for one representation and one rounding. So can we generate a single polynomial approximation that works for multiple representations and rounding modes? Google is designing bfloat 16, right, which is a 16-bit representation. NVIDIA is designing TensorFloat 32, which is a 19-bit representation. Microsoft has its own MSFE. Now, if you're a library designer, a glibc libm maintainer, will you create polynomials for all of them? From a software engineering viewpoint, it's like a nightmare. So one of the questions that we asked, that we started asking was, can we generate a single polynomial that works for everything? Okay, you may be asking, come on, as Rich pointed out, oh, there is double 64. Let me like magically design a 64-bit library. Why can't I use it for 32-bit and 16-bit? Right? That's a valid question. So that's what we've also started exploring. So you have a library for 64-bit, and now like you have your favorite 16-bit representation. Why don't you just use it? How would you use it? You have a log x to base 2 for a 64-bit double. And now what do you want to do? You want to generate a result for 32-bit input. So you have an input in float. So the types don't match. So first thing you do is you promote the floating point value into double. Every floating point input, 32-bit floating point input, is representable in 64-bit. Okay, so there is no loss of information there. And then you call the library. You'll get the result in double precision. Okay, and then you truncate it down to 32-bit. Okay, so this is a nice solution you could do if someone magically gave you a 64-bit library. But this approach does not work. Why? This is called as the double rounding error. So when you're doing 2 roundings. The first rounding happens in the double library. You're rounding a real value to a double precision. And the second rounding happens from double to float. And that changes the rounding precision. So again, like I'll show you a cartoonish figure here. So the first row indicates the double values, 64-bit double values. And the second row here shows the 32-bit double values, 32-bit float values. And the square boxes are floating point values. Okay, so and the star is the real value produced by your double library. Okay, the first thing what you do when you call the double library is it produces this real value or close to it and produces the correctly rounded result for it. Okay, and then you promote it to, you truncate it to a floating point, you round it, and it will go to a different round. So if you look at this, this star is less than the midpoint. It should have rounded to this result if you directly rounded it. Okay, so why is this happening? When you do double rounding, you're losing information about the real value, which is important for rounding. So what is this information? To do correct rounding, you need 3 pieces of information. So is the real value exactly at the midpoint of 2 representable values? The second point is the real value less than the midpoint? And the third information is it greater than the midpoint? If you have these 3 pieces of information, you can correctly round to any representation. And double rounding does not maintain it. Now the question is, can we make double rounding innocuous? So by maintaining this information. And this is our Popple 2022 paper. And I think again, I'm biased, but this is the best paper I've written in my career. Okay, so it has mathematical proofs, implementations, and it's very, very well written. And it's also used by people. Okay, so the magic for this is if you want to produce a correctly rounded library for representations from 10 bits to 32 bits and all rounding modes in the standard, what is our magic secret sauce? Create a library that produces correctly rounded results for a representation that has 2 additional bits, but with a non-standard rounding mode called round to odd. Okay, so you want to have correctly rounded a single polynomial that produces correctly rounded results for all representations from 10 bits to 32 bits and all rounding modes in the IEEE standard. What do? You create a library for 34 bits that produces correctly rounded results with the round to odd mode. Again, I'm just using 10 and 32, like it's in general. If you want to produce correctly rounded results for any representation up to n bits, so you create a library for n plus 2 bits with the round to odd mode. Okay, so now I emphasize this. Now, what is the round to odd mode? So the round to odd mode is a non-standard rounding mode. So if a value is exactly representable in the representation, it rounds to that value. If it's not, it rounds to an adjacent value whose bit pattern is odd. So let me explain it with an example.
10 to the 32 people have that many independent implementation, or is that
one implementation? You create 34-bit implementation with round to odd, and then you double round to any representation, it produces correct result.
If I only want 10 bit represent, just an argument.
Yeah, it's just an argument, like it's the final rounding at time. Okay, so what is round to odd? So I will explain it with a more pedantic example. So let's say we just have integers in our representation. Those are integers are the representable values. And let's say you get 9.6. It's a value that was produced. Now you want to round it. So 9.6 is not exactly representative. You need to round it. So what are the adjacent integers? 9 and 10. And which one will you round to? In round to odd, you round to a value which is odd. In this case, it's 9. So in 10.3, you get 10.3. So what are the adjacent integers? It's 10 and 11. Where do you round to? You round to 11. And if you get exactly 9, you round to 9. You get exactly 10, you round to 10. This is round to odd. Come in one slide. So this round to odd was not invented by us. Okay, so Goldberg has a seminal. Goldberg is one of the seminal Sun Microsystem folks who build like what every computer scientist needs to know about floating point. So he had used it for round to odd, but he did not call it round to odd, but he had used it to convert decimal fraction to binary fraction. And similarly, Sylvie Boldo had used it in other contexts. But no one had thought of it in the context of elementary functions or creating math libraries. Why? Because they were obsessed with approximating real values. They were not approximating the correctly rounded result. So as a result, rounding mode was not even their focus. So our key contribution is like putting round to odd in the spotlight and using it in the context of correctly rounded math libraries. Okay, so now coming to this point, like I'll just pictorially describe round to odd and then give the intuition. So you have 34-bit FP values. If it's exactly with round to odd, if it's exactly representable, it rounds to this value. Otherwise, it rounds to an adjacent value, which is odd. Okay. Sorry.
Exactly.
Any even number that will round, any exactly representable number in the representation rounds to that value.
We don't change it order.
Yeah. So if it's exactly representable, you got let's say if you just have integers, you got an 8. Yeah, it rounds to 8. If you got 8.1, it rounds to 9. Okay. So now, but this point, right? Like, what is the intuition? Okay. So now I'm going to describe this with 32 and 34-bit values, right? Like, so you have a 34-bit floating point, and these are the representable 32-bit values. Okay. So, and in a 34-bit floating point, you have 2 additional precision bits. So that means there are 3 additional values between 2 representable 32-bit values. Okay, those are represented by diamonds. Okay. So this is a 32-bit floating point. The values in a 32-bit floating point, and the first row is the values in a 34-bit floating. Okay. So now, irrespective of what the bit pattern in 32-bit floating point is, whether the bit pattern here in 32-bit floating point is even or odd, this value in a 34-bit will always be even. Why? Because you're just adding zeros at the end when you do additional precision bits, right? You add 2 bits of precision, this value will be even. Okay. If this is even, this has to be odd. This is odd, this is even, and this is odd, and this is even. So any value that is representable in a 32-bit floating point will be even in the 34-bit representation. Okay, first point. And the midpoint of 2 values is also even in the 34-bit representation. Okay, so now you got a star here. So what will this round to? It's not exactly representable in the 34-bit representation. It will round to a value which is odd, which is this point, which is odd. Okay. So this maintained the information that this value, the real value was less than the midpoint. That information is maintained by doing round to odd. Okay.
So when you say even or odd, you mean the last bit of the mantis?
So I think like
Is that what you?
effectively treat the entire the last bit, last bit of the mantis as 0 or 1. So just like treat the entire floating point bit string as an integer and then interpret. Okay, so it preserves this information. So now if you round this value, it rounds to the exact result, as if you directly rounded the star to a 32-bit floating point. Okay, so this is like a round to odd preserves these 3 pieces of information, which is the value less than the midpoint, exactly equal to the midpoint, and greater than the midpoint. And the proof is a bit more involved. Like I think if you really want to look at the proof, that's why that's in the Popper paper. We identify the 4 components that is required for rounding any real value to a particular representation. And the theorem that we prove is the rounding components that we have with round to odd is exactly the same as the rounding components that you would get for directly rounding the real value to the target representation. And that's why it produces correct results for all representations. Okay, so now once you have this insight, do it with generate a polynomial that produces correctly rounded result for n plus 2 bits with round to odd. Using the RLibM approach is pretty straightforward. You generate an oracle that produces the correctly rounded round to odd result of the elementary function. So in a representation with 2 additional bits. So no one had this oracle, we built it. Because no one had used round to odd earlier, right? So we build this, and then what do? We create the rounding interval. Okay, and then one caveat that you need to do, that you need to address, is if the elementary function produces a result that is exactly representable and is an even number, then the rounding interval is a singleton. In the odd, with the round to odd mode, if the value is exactly representable, it just rounds to the even number, just rounds to that value. So the result is a singleton. Okay, so now generating polynomial approximations with singletons like constrains the polynomial generator significantly. But fortunately, we can frame a mathematical problem out of it. Okay, so what is a floating point input? It's a rational input. the value is exactly representable in floating point. It's a rational output. So, and the result is even. So what are we looking for? We are looking for inputs, rational inputs that produce rational inputs to elementary function that produce rational outputs. And this is Lindenman has like studied this problem for a long time. This is the advantage of working in an area where like people have built history of work, right? So we can use results from them and do this. And just to give you an example, like what happens with log x to base 2? So when would log x to base 2 produce an even integer? When x is 2 to the power of I and I is even. In those cases, you will be singleton. And then we can identify those cases using bit vector operations and easily produce results for them. So we remove the singletons. Okay, so what are we left with? We are left with other rounding intervals. We generate polynomials and we solve them. There you go. Okay, so what do we have? We have a single polynomial, okay, that produces correct results for multiple representations and multiple rounding modes. So this is what I'm saying. The result is you have your B float 16, your tensor float 32, and your float. They have different rounding intervals if you just specifically looked at them in isolation. But by producing a polynomial that produces correctly rounded results for 34-bit with round to out, it produces correct results for all of them. So we published this paper at POPL, and since then we have been trying to push developers to adopt it.
So wait, is this- so the library always computes the 30, like, let's say 34-bit representation, and then at the last step,
Yeah, so if you want to use,
it goes down to the lowest.
yeah, so effectively this is exactly like the 64-bit library case that I talked about, right? If you had a 64-bit library, why don't you use it and then produce a result for 32-bit? It did not work because of double rounding error. But with our approach, we produce the result for a 34-bit library.
This approach, like architecture perspective, right? I would want, all my functional units to be 16-bit instead of 34-bit.
You're right there. Like this is fantastic audience, right? Like you are thinking my mind.
The very last step.
Thinking my
I
mind.
get the advantage, well, except for storage, I don't get the advantage.
Yeah, so thinking minds, like, so what happens with our approach? It's great, like intellectually very interesting and like helps developers, right? But lower bit widths, the 16-bit representation pays the cost of the 32-bit representation. Can we do better? And this is where we propose progressive polynomials. So a single polynomial produces correct results for all representations and all rounding modes. And then if, let's say, Rich is excited about his 8-bit representation, he just uses the first few bits of the first few terms of the polynomial, and his polynomial evaluation is much faster. Okay, so we call such polynomials progressive polynomials. And doing it with our approach is very simple. When you generate a linear constraint, just discard the constraints. And like you're generating a system of linear constraints, and all constraints need to be satisfied, you automatically get this property. So this is our notion of progressive polynomial. So you still have the entire polynomial that works for everything. And if you have some custom representations where you want to be very fast, you want to have better coefficients like 16-bit coefficients, or you want to use fewer terms, you can directly incorporate it. Okay. So the last part I want to talk to you is like, this is all cool. We generate, how do we solve this LP problem? And Badri pointed out, and Sefer is nodding here, like Sefer helped us out with some of it. So you have a large LP problem. And with progressive polynomials, you are adding more constraints. How do you solve it? So the key observation, as Badri alluded to, was the LP problem, the linear program that we generate is a linear program of low dimensions. Even though we have billions of constraints, we have very few variables. But modern solvers are not tailored for it. They just time out. Okay. Yeah. So they're just tailored for balanced dimensions where the dimension and the constraints match. Okay. And this 4 billion is a lot. Like they run out of memory most of the time. Okay, so we design, again, there is a fantastic algorithm by Clarkson in the Journal of ACM 95, and we wanted to use them, but we couldn't, we had to adapt it to our context. So I'm going to give you a sketch of the algorithm. So how do you solve billions of constraints, right? So these green bars that you have are all the constraints. You want to generate a polynomial that goes through all of them. Okay, you can't give all these constraints to the LP solver because it times up. So the idea is, it's a randomized Las Vegas algorithm. The idea is you sample some constraints from it. Okay, and then you generate a solution for the sample. And hopefully, if it satisfies all the constraints, you're done. If it doesn't, you have, so some of these constraints will be violated. In the next iteration, you want to choose them. Okay. Now, how do you design a protocol to choose them? Okay. So we use weighted random sampling. So initially, we assign weights to everyone, a weight of 1 to everyone. So there's uniform probability of choosing all of them. Okay. And then we sample. Okay. The blue bars are the ones that we sample. And we use an LP solver to solve the sample. Now, just to give you an idea of like the difference, so we had 4 billion constraints, and K is the rank of the system, the number of terms in your polynomial. So it's K minus 1. If the degree is K minus 1, you have K terms. So we would sample 6 K square constraints. Okay, so typically our degrees are 5, so it's 150 constraints. That's what we are sampling. And then we solve a sample, and modern solvers can quickly solve 150 constraints. Okay, so and why is this 6K square? This comes from the bounds that we want to have on the number of iterations. So from constraint sampling lemma. Okay, so we sample 6K square constraints. So the resulting solution will satisfy all the points in the sample. And now we evaluate it across all the candidates, all the intervals that we have. As long as it satisfies significant fraction of the constraints, we call such iterations lucky iterations. Okay, so and for any of the violated points, we would double their weights. In the next iteration, we want them to be chosen. Okay, so we repeat this process. So we throw away the sample and we double the weights. The only thing that that is maintained is the weights. So now we do weighted random sampling again, and we choose a new sample, generate a polynomial, and it will satisfy a large fraction of them. And then, so there'll be some violated points, double their weights again, and redo the process. And eventually, yeah, you generate a polynomial that satisfies all the points. So again, the details are in the paper, we have a proof. So this algorithm solves when the system is full rank. It solves, this randomized algorithm terminates in 6K log n iterations, where K is the number of terms in your polynomial, and N is the total number of constraints. And this is a worst case form. In practice, we do it like in 600 iterations, we can solve like 4 billion constraints. So it's much faster in practice. Okay.
Do you have to go back and check all the constraints later? I mean,
Yeah, so we check it, like there is always like there's a satisfaction process, right, where we adjust the weights. Okay, so this iterative algorithm it was instrumental in us generating a single polynomial that satisfies all the points. So initially, when we started the RLM project, we're generating piecewise polynomials. We did not know of an algorithm to do it. And sometime around like 2021, last year, like we were trying to read Clarkson's method, and I was totally lost in the woods. And that's when like, having a colleague like Sefer and picking his brain was really useful. And he helped us walk through everything, and then we implemented it, and there we go. We had like amazing results.
well, there's no guarantee that that's going to work, but I would imagine for the elementary functions are not bizarre, so probably it will find it.
So I think like the premise is like the system is full rank. If it is not full rank, you'll generate certain violated points. Like we can take this.
Yeah, we'll take it off.
Yeah.
Okay,
So now the question is, it's probably, I don't know, like what do you mean by it's not?
Well, no, if the function you're trying to compute has some totally bizarre shape, this sampling may not actually find it.
No, so the
Valid set of constraints.
so there is range reduction, and the way we do it is like we constrain the ranges. And the definition of full rank indicates there are 4K basis vectors for the constraints you model.
Well, we'll take it off. Imagine you had a function that always like squiggles in it or something.
Yeah, so you smoothen it out.
Necessarily find it, but the functions you do.
Yeah, those are full, those are not full rank, and typically in machine learning they are called as like non-separable problems. So there's no hyperplane that actually separates both these points. Okay, so all this entire story was like me telling me stories, right? Does it work? And we built a collection of elementary functions. So at the time when we wrote the paper, we had 10 functions, but today, like I had an amazing student, Sayuk Park, over the summer, he got another 9 functions where we are writing a paper on. So a single polynomial produces correct results for 805 configurations of which is representations and rounding modes. And it's correct. So it ranges from 8 bits to 32 bits, all representation that you can think of. Okay. So now the question is, just to give you an idea, how do others fare? Like people have, like Intel has invested decades of work to build this, right? They all produce wrong results. And people have built correctly rounded library. CRLibm is a correctly rounded library, but for one representation, double. And when you repurpose it for other representation, it produces wrong results. Okay, so the moral of the story is we are correct for all inputs and multiple representations with a single polynomial. The next question is, that's all good. Like probably you're paying in terms of speed, right? So this graph, I'm going to show you the speed up of RLibm functions compared to the corresponding Intel functions. So on average, Intel's functions, RLibm functions are about 30% faster than the corresponding Intel functions implemented with floating point, 32-bit floating point. So Intel's functions produce for 4 billion inputs, it produces like 500 million wrong inputs, wrong results, 500 million wrong results. So in contrast, we are fast and also correct. And if you use the double library that Intel has, it's slightly accurate than the floating point library, but still produces like 100 million wrong results. And we are still faster by 50%.
Dave Pack has a question.
Yes.
Dave, do you want to ask your question?
Sure. I just wanted to check, like, is your method always correct? Like every time, even it gets the tiebreaker correct every time? I mean, that seems pretty hard.
For all inputs, for like, if our algorithms and if your proofs are all correct and your implementations are, unless there are bugs, they will produce the correct results for all inputs on all machines, as long as your machine is IEEE 754 compliant.
Great. Wow. Thank you.
Okay. So the next thing is like, how do we compare to other correctly rounded libraries? CRLibm is 2 decades of work by John Muller's group in India, and we are like 3x faster than. Okay. So all this is great. Like we write papers, but like what has been the most gratifying piece about this project is like getting to collaborate with industrial maintainers, and we have pushed 5 functions from the RLibm project into LLVM. It's now in practice, used by billions of people. So it's exactly like we code reviewed it, and we made the developer push the various algorithms, and they're fast and correct. So again, this is a math library has 33 functions. If I'm successful, maybe in a year or 2, we will have a correctly entire collection of 33 functions, and we'll push it. And I'm collaborating with the Intel team now to push correctly rounded functions into Intel's library. So hopefully, like we can mandate correct rounding in the next version. Okay. So what are the key things I want you to take away? 1, if you're developing correctly rounded implementations, directly approximate the correctly rounded result. There is a set of real values around the correctly rounded result. That is your freedom, and you can frame an LP problem, and that gives you a lot of freedom and to generate really efficient implementations. And if you want to have a single polynomial approximation that works for multiple representations, design a correctly rounded result for a representation with 2 additional bits with a round to odd result, and that magically produces correct results. Okay, so perhaps like we are given a lot of evidence to the standards committee to mandate correct rounding for elementary functions. So I'm collaborating with them, and hopefully in when the 2029 standard comes out, the standards have a 10-year lifespan, so we will have correct rounding. So that said, I do a lot more work than whatever I've talked about today. So these are my graduated PhD students, like JLM was started this project, but Sayuk is continuing on issues and doing really cool work. So Matan is my newest PhD student, and Sayuk is my first year PhD student, and Hari is a PhD student that I co-advised with Srinivas. So I have a lot of other cool projects. Like one of the projects that I'm talking to about is crypto verification with Leo. I used to collaborate with David Cash. We have some NSF funding like there. And Correctly Rounded project is a joint work with my former PhD student JLM, who's now a faculty member at Yale, and Mrudul Anjaneya. I have projects on formally verifying the entire eBPF ecosystem. This is with Srinivas Narayana. I have a long-standing project with Rich Martin on accelerating programs on FPGAs. That said, like these are the current projects, but I've also collaborated with Ricardo, Tu, Vinod, Leviu, Costas in the past. So I've learned from them. And I think like one of the cool things about being surrounded by faculty, so you can just knock on their door and get inputs. And my experience with collaborating with Safir and picking his brain is one example of this. So with this, I would like to take questions. Yeah, I'm trying to convince him.
Very good, and I see a lot of impact of your work. So definitely put pressure on the math. One question, very for scientific discovery. You are more a program. How did we end up in this part of boundary line of computing?
That's why, Badri, I wish you were like 5 minutes early.
How did you end up?
Well, I told a complete story. So I was working on compiler verification, and my student David Menendez built like a lot of these DSLs to verify compilers. And compilers deal with floating point, and there are two kinds of floating point. One is optimizations. One is like bit precise optimization. The other is fast math optimizations, which is like any real.
More an evolution.
And we had to like, we saw math libraries were producing wrong. We had to figure out what was wrong. And at that point in time, we had to like, I had no background on approximation theory. I had to acquire it, and we took it as a challenge and learned it.
Fantastic. Your work is being discussed on Twitter and everything.
Yeah.
No, I mean, amazing. First of all, that Linux development.
Yeah. So there is
Linux thing was amazing.
so that's courtesy like the students Harishankar, Vishwanathan, and Matan and Srinivas. So we had like there is a kernel component called BPF. And BPF is like revolutionizing Linux kernel in whatever, like, but there is a static analyzer part of BPF. So static analysis uses a lot of abstract domains. We proved like one such abstract domain, TNUPs, and we designed faster algorithms for doing it. And we showed that it's faster than the Linux kernel, and it's correct. So we pushed it.
Yeah.
And again, this is students, Srinivas and Hari and Matan also deserve equal credit.
Still, in fact, very good. Very proud of you.
Yeah, I just have one, I'm curious on your thoughts on I'm not old enough to remember, but back in the day, every vendor had their own floating point implementation, and it made software development this nightmare because it would work on, like I wrote it for, just like in your example, like I got to work on this machine, and then I recorded this other thing, like toy breaks.
So
And then I can't trust the code really. So that was this like nightmare world, and then IEEE 754 came out and kind of made it so that people, especially students, you don't think about that anymore. Okay. So are we going maybe back to that world a little bit with all these 40-foot stations?
So I think
I mean, your stuff mitigates some of it, but
yeah. So if again, like IEEE 754 was a compromise between various companies so that it could ensure portability. So right now, like people want immediate results in the sense like Google wants like their machine learning algorithms to be very fast, and like moving data is costly. So standards have a very slow update cycle, 10-year period. So right now, like floating point representations is like the wild world out there. But again, so one of the like, there are a lot of things like how do you provide freedom for innovation while standardizing? This is the delicate line that you need to draw. And I think there is a lot of flexibility in the standard. Like standard does not mandate. It says like these many exponent bits, these many mantissa bits. You can parameterize it and run it. So the challenging parts come in when you're implementing multiple rounding aspects of it. So hardware vendors prefer round to zero. And standard, that's one of the acceptable rounding modes in the standard. So how do you reconcile all this? So due to conventional wisdom, the standard did not mandate correct rounding for elementary functions. Why? The conventional wisdom was it's infeasible to generate fast representation. And our evidence, what we are showing is you can be fast if you like decouple the problem into the problem of generating the oracle and the problem of generating the efficient implementation. So any more questions?
I don't see any questions.
Okay.
So cycling back, like, is it now possible to verify some of those fast math optimizations if the math libraries are correct?
So you can at least like debug them. Like we have my other students have built tools. Like Sangeeta has a paper coming at UPSLA where she has built tools to build shadow execution. We can debug them. Fast math is still like you can debug it, but you can't reason it. Like verify typically means you have to prove for all inputs. But at least what we can do now is for a particular input, you can pinpoint and say what is going wrong. And how do you do this statically for all inputs? It's still an open challenge.
And well, as always, Santosh is around.
Awesome. So I will stop the recording now. Thanks everyone on the Zoom call for attending.